Okay. So scaling deep learning with data parallelism. Hopefully everybody here is already convinced that deep learning is a powerful tool in science as well as all kinds of industry workloads. But over time, as the field is maturing, as people are using deep learning to tackle harder problems with larger data sets and using bigger models, the computational requirements, in particular of training these models, is growing. Growing even exponentially, actually. So this is a little bit of an older plot here on the right from OpenAI, but it just shows this exponential growth over time in the compute costs to train popular deep learning models. This shows two eras. There was kind of a traditional machine learning era and then a modern deep learning era on the right. And as you can probably imagine, there's been a third era with the recent explosion of LLMs. It's not shown on there. But it's nonetheless still like an exponential kind of growth in cost. You might have also heard about like growing costs in inference, like in the LLM space, inference scaling. But today we're mainly talking about training models. So these results are, not so much science focused. These are just models on standard benchmark machine learning problems. But we do know that in the science communities, there are also growing compute requirements for machine learning. We do things like survey the NERSC users. You might have seen our emails asking for your input on our machine learning at NERSC surveys. So thanks to everybody who fills those out. But from things like that, we know that while there's a pretty broad distribution, we have a lot of scientists who might have moderate scale problems. Maybe they can train on a single device in hours and have maybe just like tens of gigabytes of data. There has been this growing tail in the distributions here of people who basically it's just impractical for them to train a model on a single device because it might take months. And they have data sets that are, tens of terabytes or larger. So if you're trying to solve a problem and you need to train a model, it's going to take months to do it. There's a good chance you're just not going to bother, right? So we need to find ways to speed that up. Therefore, we need to scale deep learning. We need to make use of our computational resources like those at NERSC in order to be able to rapidly iterate on our research and hopefully enable scientific discovery on the most interesting problems. Okay, so we're going to do that today through parallelization. There are a few different ways, several different ways to parallelize the training of a neural network. But usually you can kind of think of these in two broad categories. So there's data parallelism and model parallelism. Data parallelism is the simpler case. And this is where you're parallelizing over the data dimension. So if you think about doing stochastic gradient descent where you're sampling a mini batch of data. In data parallelism, you're taking that mini batch and now you're splitting it up across multiple GPUs or TPUs or nodes and stuff like that. And kind of as the diagram shows here, you're actually replicating the model across all those devices. So you have a full copy of the model that's always the same across all your GPUs. They're just each looking at different subsets of data when processing these mini batches. Okay. On the other hand, you have various forms of model parallelism, which in this case, instead, you're actually parallelizing the computation of the model itself. There are various ways to do that. So these pictures show you a couple. The first one here is one that you might call tensor parallelism, where you can see that actually different, like a layer of a neural network itself is parallelized. So if you think about that as doing kind of a matrix multiplication, you're splitting up. You're basically using parallelized linear algebra, doing things like a distributed matrix multiplication there instead. Then on the right, this shows an example of pipeline parallelism, where you might actually put different layers of a neural network on different devices. Okay, and then when you're processing data, data is kind of flowing through these in a pipeline fashion. Data parallelism is usually the easiest thing to implement. The tools and libraries today make it very easy. You'll see a little bit later, really just a few small adjustments to your code. And it's the most commonly used thing. In fact, if you can get away with data parallelism, you should probably just stick to data parallelism. And again, that's the focus of this presentation. We're going to kind of show you how to do that. Okay, but how does this actually accelerate the learning process? I think it's helpful just to kind of review how stochastic gradient descent works just a little bit. Okay, we didn't cover that yesterday, but hopefully you've heard about it before or encountered it a little bit before. But in SGD, and this is really just like vanilla SGD, this formula shown here, this is not including momentum terms or other things you might find in more modern optimizers, but conceptually it's good enough. So when we're doing SGD, what we're doing, right, we have some objective function, a loss function. We're running data through the model, we're computing a loss, we're computing the gradient of that loss with respect to our model parameters, our weights, okay? This is what tells us how to adjust our weights to get a small improvement in the model, in the loss, okay? Minus sign, so we're actually doing the direction of steepest descent. We're summing over all the samples in a batch, we're actually averaging over all the samples in a batch, and then we have a step size parameter, eta, which is your learning rate. All right, so this is not really representative of what it looks like with neural networks. This is a convex, very straightforward optimization problem. But anyway, the idea is we're taking little steps and hopefully trying to get to a minimum in the loss space, right? Can anybody tell me why, when we do stochastic gradient descent, we actually like to use small batch sizes? If you're on Zoom, I guess you could just type it in the chat if you want. Or people in the room. I'm gonna ask you questions a few times to get you thinking.
I think there's two reasons. First one is we want to avoid some local minimum. Second one is like sometimes we cannot really put large batch size into it.
Yeah, did you use the word noise at all? You said we want to avoid local minima.
Right.
Local minima? Okay, that's something. I kind of gave it away by asking if you said the word noise.
Okay.
Did anybody have another answer?
Faster to update the weights from like single.
Yeah. So I think there's kind of two reasons. One is that, for the amount of computation, we're doing more steps if you're using smaller batch sizes. But the one that I think is important for what we're going to talk about today is the importance of noise. So small batch sizes will introduce variance in that estimation of the gradients. And that turns out to be really important for generalization. You actually want to do kind of a random walk while you're optimizing a neural network. Otherwise, you might end up very sensitive to the landscape that you're optimizing on and essentially overfit. Okay, so how can we speed this up? This process of taking these little steps to get to an endpoint. Well, we can do that by taking fewer, bigger steps and taking them faster, right? So like parallelizing them. In practice, what that means for data parallelism training, we're going to try to push to larger batch sizes. We're going to use larger learning rates, and we're going to parallelize across more GPUs. That's it. If you want to just leave the presentation now, that's what you need to know. But there are big limits to what you can do there. You can't just arbitrarily increase the scale of these things. Okay, so kind of already gave away the answer for one reason why, which is that actually we like to have noise in those gradients. And if we go to really large batch sizes, we're essentially reducing that variance, reducing that noise. We're getting a more precise estimate of the gradient, but it means a more precise one that corresponds to the training set, not necessarily our test set. But you can probably imagine that there are other limitations here. Like what happens if you just use an arbitrarily large learning rate? You can just skip over the minimum you're trying to get to, right? So that's just like your model just completely diverged, and you would see that it should be obvious. But the other case might be a little less obvious. Okay, so how do we actually parallelize this process? So in the forward pass of a model, it's basically trivial. So we have different subsets of our mini batch across different GPUs. And after you do, the kinds of matrix multiplications that you have in a neural network, it just works out of the box that, across all GPUs in the end, each one has their own full copy of their outputs, right? But when you, and so no communication is necessary in the forward pass of a data parallel training. But when you go to implement the backward pass, now we're, computing the gradients at the output and kind of working backwards through the network. So we're doing a step where we're computing the gradient of like the previous output with respect to that, the previous layer with respect to the later layer. And then we're also computing the gradient with respect to the weights. But when you're computing this gradient with respect to the weights, on each GPU, you don't actually have the whole answer. You have these kind of partial answers. And so you actually have to insert an all reduce here so that everybody sums up the gradients from everybody else. And then in the end, all your training ranks have the same answer and they can update their model in the same way. Does that make sense? So there's essentially one communication call here, let's say per layer, right? It just needs to call an all reduce, which is a fairly simple operation in terms of high performance computing. And you can also hide a little bit of that communication with these other computations.
The question in Zoom.
Yeah, maybe you guys can take a look at that. Or we can try to answer or take a break and let people ask questions in a little bit. Okay, so as you're scaling up, there are kind of different, a couple different ways that I think are useful to think about how you're adjusting your batch size conceptually and what are the consequences of that. So you might consider a case of weak scaling versus strong scaling, okay? What I'm calling weak scaling here is where you're scaling up and keeping a fixed local batch size. So on every GPU, you have some batch size, let's say it's 16. And then as you scale to 4 GPUs, your global batch size is now 4 times 16 or 64. So global batch size is just, number of ranks times your local batch size. A nice thing happens when you're doing that. Basically, the amount of compute per device is the same, right? So your ratio of compute to communication is pretty good for scalability. However, as you're scaling up in that case, your batch size is getting larger and larger, and then that can impact convergence, the things that we kind of already talked about. On the other hand, you might think of strong scaling. Maybe you have a global batch size and you want to keep that fixed and now scale up to multiple GPUs. So if you started with a batch size of 64 on a single GPU, you're going to 4 GPUs. Now each local batch size is 16, okay? The advantage of this is that the convergence behavior should essentially be the same as what you ran on a single GPU. You have the same global batch size. There are some caveats to that. If you're doing something like batch normalization that relies on local statistics, then those local statistics are changing if your local batch size is decreasing. But usually in practice, that's, I think, more like a second order kind of effect. But a bigger thing you have to worry about here is now you're reducing the amount of compute on each device as you're scaling up while increasing the amount of communication. So at some point, communication is just very likely to become a bottleneck, okay? Might depend. So if you're just scaling out to 4 GPUs on a node where the communication between GPUs is fairly fast because of NVLink or something like that, maybe it's no problem. As you start scaling across nodes, it might become an issue. Okay, and then of course, there's a very fundamental limitation with data parallelism of how many GPUs you can use, which is just the size of your batch, right? So if you had a batch size of 64, obviously the most GPUs you could parallelize that over in a data parallel way would be 64, right? Obvious, okay. Okay, but that's not all. You can't just increase batch sizes, increase the number of GPUs and expect everything to go better. You might see some difference, but you also have to tune things like the learning rate. We want to actually take advantage of having larger batch sizes to be able to take larger steps in optimization. In practice, you're going to just have to find out what the right learning rate is. Unfortunately, the answer in deep learning is often just, you're going to have to check to see what's the right answer for your use case. But there have been some rules of thumb that you might find useful to think about for how to adjust the learning rate. So the first one here is the linear learning rate scaling rule, which is a very intuitive kind of one, and it's the ideal case that you would love to see. So imagine if we're taking, instead of 3 small steps, we want to take 1 step that's 3 times as large, right? That's like giving us basically a 3 times speed up, right? So we would want to increase the learning rate by the same factor that we've increased the batch size. Okay, but if you actually take a look at if you actually think a little bit about the statistics of how the variance would change as you increase batch size, since it depends on this 1 over batch size, that actually motivates more of a square root learning rate scaling rule. So if you were to increase your batch size by a factor of 4, you would increase your learning rate by a factor of 2. Okay. It turns out neither of these is really the right answer, especially when you fold in like the idea that you have to generalize to test data sets. This is a little bit of an older result, but it still kind of applies and demonstrates the fact that actually just sort of depends. So this was an OpenAI paper actually, but they showed that, depending on where you are on batch size, you might be able to kind of be scaling up in a linear fashion. At some point, it might become more like a square root learning rate rule that you need to use. And of course, obviously, there's some ceiling above which higher learning rates are not going to give you any improvements, so it does plateau out. Should probably be watching the time. Oh, wow, okay, gonna speed up a little bit here. Some of this has kind of already been hinted at, and these are just sort of demonstrating things like the issues that come up with generalization, so I think I'll go pretty quickly over these, but you can go into the links, the references on these slides if you want to learn more. Basically, there was a paper that saw that particularly in the early stages of training, having large learning rates is unstable. That's because things are changing really rapidly. Like the picture doesn't look like this, where that one big step is kind of approximately close to where the three little steps would end up, right? Because the gradients are changing so much in the early stages. So this paper basically, well, no, there was a later paper that I'll get to that argued that you should start with a lower learning rate and ramp it up, okay? You know, people started to look at what's going on with this generalization gap, why you might be doing well on the training set and not the test set. And the idea is that, you know, you want to end up in these large flat minima spaces of the loss landscape. But if you end up in these sharp ones, then any deviation between the training set function and the test data set function gives you a huge penalty. Okay. This work actually showed this by looking at the eigenvalues of the Hessian, basically just looking at how steep the loss landscape is when you come to convergence, and for smaller batch sizes, it was more flat, and larger batch sizes, it was steeper. So it just kind of confirms, gives us an intuitive sense of what's going on. We're overfitting in these cases with large batches. We're ending up in these sharp minima that are very sensitive to any, you know, differences between the training and test data set. Okay, yeah, this paper here showed that you can get some pretty big improvements if you do a warm up of the learning rate. So start with a low one, ramp up to your larger scaled one, and then proceed with your usual learning rate decay schedules. A couple papers looked at the limits of batch size scaling and actually were able to see this kind of relation of the largest like good batch size called the critical batch size to the amount of the noise in the gradients. So if your data set is particularly difficult and noisy, you might be able to get away with using larger batch sizes, that kind of thing. There's an extension to data parallelism, which is kind of in between data and model parallelism in some ways, but it's still fairly easy to implement. And so it's something that you might find useful in your cases. It's called sharded data parallelism. So basically, if you look at standard data parallelism, there's a lot of duplication. We've replicated the entire model and any sort of states that are in the optimizer across every single GPU. You don't really need to do that. And it turns out it's pretty easy to just start sharding some of those and then just communicate them to where they're needed when necessary. So sharded data parallelism is just basically different levels of doing that, sharding different things. It's simpler than model parallelism. You can use it very easily in PyTorch, which is a different wrapper. Instead of DDP, there's an FSDP wrapper. And the communication costs are not too bad. They're not going to be as heavy as you'll see when we get to full tensor parallelism later. And you can basically get like really big memory savings. This is not necessarily going to be super effective in every kind of case that you're studying, though. This is particularly effective if you have a model where a lot of your weight is coming from the number of parameters in that model. So if you have a lot of parameters in a model, that's consuming a lot of your memory. By sharding those kinds of things or sharding the optimizer weights can save you a bit. If you instead have a problem where maybe your model doesn't have that many parameters, but you're consuming a lot of memory just in activations. For example, if you have a really high resolution image that you're using a vision transformer on, which basically turns it into a very long sequence length, now you're going to be consuming a lot of memory because of that, you know, like quadratic complexity of attention. And this won't help you as much in those kinds of cases. Okay. But it can effectively let you do things like train a trillion parameter model without using model parallelism. So that's up to you to decide if the trade-offs are worth it. I'll skip this up about MLPerf, but if you want to look at kind of state of the art in speed of training models or MLPerf benchmarks, okay, the code ingredients to implement data parallelism, you'll see them today as you look through the code and go through the README, but it's essentially just a few things like this. You're going to need to initialize the communication libraries. You're going to wrap a model in this special PyTorch wrapper called distributed data parallel, or people might call it DDP. You probably want to shard your data loading. You can use this distributed sampler so that within each epoch, every rank is going to sample only from its some subset of the data. And then you're gonna launch things in some way that you'll have one Python process per GPU. Okay, so on Perlmutter, we have 4 GPUs per node. So you're gonna run basically 4 Slurm tasks per node. Okay, some very quick performance considerations. When you're doing any sort of parallelism on an HPC system, you're gonna make sure you're using the right libraries that are appropriate for that system. So on an NVIDIA system, you're most likely going to want to use Nickel, which is NVIDIA's communication collective library. That's going to be the best for systems like Perlmutter. There are communication settings that you can tweak. I don't think we get into them too much today, but if there's something that you want to play with in the hands-on to see the impact, this is a good thing to play with. So this DDP wrapper has a bucket cap size, which is essentially it's trying to combine some of the gradient tensors before calling a all reduce. So it just doesn't have to call as many all reduces. And so you can play with that parameter size there. IO at scale is an issue. We're not going to get into that much today just because of time and the amount of content we have. But things like big parallel file systems are not super great at like many small reads, random reads that come with large scale training. Things that you can do if you're running into issues there is try to stage data onto the nodes first, into RAM or onto SSDs. Okay, that's basically the end of my presentation. Distributed training can be imperative for some of your problems in order to make it practical to train in a reasonable amount of time. Data parallelism is pretty simple. And again, if this can solve your problem for you, if you can get away with it, if you don't need to use model parallelism, you might as well just stick to data parallelism. But there are these things you have to worry about. So large batch training could be unstable. You might have generalization issues. You might have to tune your hyperparameters a bit. And yeah, that's it. So I'd be happy to take any questions before we dive into the hands-on. Any questions from the room? If you're on Zoom and you have a question, you can raise your hand or just unmute probably.
I have a very quick one. So for your experience, for weak scaling and strong scaling, which one do you think is more common to use?
Which is more common?
To use?
It just depends. I think what you might end up doing if you're trying to scale out and speed things up is probably some combination of the two. So you might use weak scaling for a bit until you find, that you're not getting the benefits that you expect from increasing the batch size. And then if you really need to make it faster, you might strong scale a little on top of that. But then you have to understand that there are the trade-offs that you might be reducing your overall efficiency of using those resources. You might double the number of GPUs. Actually, in both cases, really, you might double the number of GPUs. You might not get a 2 times speed up. So you have to kind of keep those things in mind as you're, yeah.
I have a hard time understanding why the learning, you have to adjust the learning rate when you change the batch size. I don't see.
Yeah, so
I mean, if it's just purely because you wanna take advantage of the speed up you get by changing the batch size, or like you get different answers when you change the batch size and that's where you wanna adjust the learning.
yeah, so it's kind of a couple things. So partially we're trying to make the learning rate as large as possible in order to take the biggest steps to get to the answer to make it faster, right? We're also taking advantage of the fact, and there's some tension here, that when we have a larger batch size, our estimates of the gradients are more precise. So we can take advantage of that and actually take larger steps. We're more confident that it's going in the right direction. Of course, the caveat there, the tension comes from the fact that we're potentially overfitting more to the training data set. But, at the end of the day, we're just trying to make things train faster. And so.
So you're basically, the way you calculate the loss or the gradient in the loss changes when you change the batch size.
The way you're computing the loss changes.
Sorry, I'm not extremely familiar with everything.
Like the variance in that loss changes because you're sampling from a larger number of samples, right? When you're computing a loss, you're usually averaging over the samples in batch.
Your batch is still gonna cover the entire thing, right?
After you do one full epoch of training, I guess, yeah. But if you're using larger batch sizes, you're taking fewer optimization steps per epoch of training.
Getting there.
Okay, yeah, yeah. Hopefully, happy to talk more. Is there anything like on Zoom that I should answer?
Yeah, it's kind of related to that. There's a question about if you use 4 times GPUs, the results be different when all the hyperparameters.
If you use 4 times GPUs, all the hyperparameters are the same, but what about the batch size?
Yeah.
That's the
Just
kind of
wanted
the
to clarify that.
follow-up question. Okay, if you're using the same global batch size and you're just parallelizing across more GPUs, you might be fine with the same hyperparameters. Yeah, so the caveat that I mentioned before, though, is if you're doing something like batch normalization, which computes some local statistics of the activations on that layer. When you're using a smaller local batch size, then obviously those statistics are different. There's more variance there. So you might have some impact in learning from that. There is distributed batch norm, which would actually fix that issue, but you incur more communication costs. If you are letting the batch size change, but you're not adjusting anything else, that can impact learning, and it may not be super obvious how. So basically your gradients are going to be more precisely tuned to represent the training data set. You might be more prone to overfitting, and you may not see any real speed ups. You may not see any benefit if you're just increasing batch size and not adjusting learning rate. But it kind of depends on where you start from.